things. So that way you will get a better idea of what we are talking about today. And we just reviewed what we did Monday, and now today we're going to move on a little bit further down the road such a way that you will get some ideas how do we do that, these commutators. So last time we did a commutator of the as I showed on there. Let me see where we are here. We have commutators, and so we have how to large case of this meaning. So that's n over here, and have commutators, and we already have properties of operators. And this will be item number 2. Here we're going to show you how we are going to use these commutators, how to find these commutators, and what's the consequence of those ones. And this becomes really important. So this will be item number 2. Item number 2, we want to find A, B equals what? In other words, how do we find A and B? These are both all operators. How large, what that is, how do we find this? And this is our job for today, do the calculation. Originally, I thought I'd just let you guys read the example, but I decided maybe illustrate it first. So this is how do we find them. And in this case, when we try to find how large this one is, we always have to assume a function f like this. And you may wonder, Dr. Shen, you already have A and B. Why you need anything extra on this? It kind of looks strange. I already gave you A and B. Why just tell me how large that is? Why need an extra F on that? Here's a reason why this happened. Let me show you what happens if my the A is the position operator, and this of course equals x. Let me B is the momentum operator x hat, like this. Okay. Assuming we have these two operators, A and B, in this particular format. Now A, B, this commutator is just A hat, B hat minus B, A hat like this. Okay. So that's what I did. I just simply have this one. Now let me plug these two into this equation. Let me plug this into this equation. So here's x, so first it will be x, and b will be negative I h bar partial x. So first term we are happy in the sense that essentially the partial derivative in front of the partial derivative we have x and these coefficients. This is perfectly fine. You can do it without using that f at all. Now the problem with the second term. Let's look at the second term. Second term is b in the front or the px in the front. So essentially I have a negative IH bar partial x. And this A is x. This A is x. First term is fine, but second term has a province. If I take a partial derivative, this entire term will equals IH bar. There's no question about it. But this, remember, this guy is an operator. In other words, when you did this, you are assuming the remaining terms all constant. Let me write this down. If you do like this, you have assumption. You have assumption. There's no function after x. So this is assumption. In other words, if there's no function after x, you perfectly can do this without any problem because that's the only term you need to do it. So this is perfectly fine. But this is usually not true. You cannot do like this. because this operator itself is going to apply it on any function afterwards. So this assumption is untrue. So I put a question mark on this. So because of this reason, that's why we cannot simply use these, just plug in this operator and do the calculation. Did you guys get it? Did you get it? And this is very important. And so in many cases, you actually can plug it in, but not always. So that's why it's not a generic. And I'm going to show you why. So in other words, this one is questionable. So I'm going to put a star on this. This is the questionable. You can reason in it, but you cannot directly use it. The reason was that is because these are the operators. You will have an extra term comes out, and I'm going to now show you why these extra terms comes out. So this extra term is over here. And this extra term is coming out in the following way. So we're going to assume in the function, now this function has to be, depends on the variables. So let's get a variable x like this. It has a variable x in it. So for instance, you see, if I take a partial derivative like this, x, so this function has to have x in it. If you have a y in it, then it doesn't matter because it's a constant with respect to partial. So it has to be a function of x. If you have two variables, for instance, one is partial x, one is the partial y, and then you have to be f of x and y, like this. You cannot simply put a constant behind this, because then it's not universally correct, because you cannot say, I put a constant there and you get me the results, and that won't work. So this won't work. So that's the main reason. Now let's see how we actually do it. Well, we do the following. A hat, B hat. So A hat, B hat minus B hat and A hat and times F. So then what we calculated, we first calculate A, B hat on F. Second term is going to minus B, A hat on F. And then when we do the finished calculation, we will end up with a number, which we don't know yet, and times F, like this. This box representing whatever you end the results is going to be. And then the commutator, now A, I don't want to jump at all, so I just want A hat, B hat, minus B hat, A hat, equals this box, like this. So that's the key idea of which you're going to see me to write. And this is essentially will be used in our entire derivation, and we do that. So now we're going to show you with the x and px as example. Now I'm going to start with this one. So first, let's start with A, B in this format. So my A this time, according to our example, will be x. My B, according to our example, is negative I, h bar, partial x, and f, like this. This term here is just this term. Let me call it small box 1. You know this small box 1? Small box 1. This term is just this term. And this that's what we have. Okay. And then this term you cannot do anything with it because you don't know the function, so you just leave it as it is. What we can do is the next box, let me call it box 2. So now we're going to work on box 2. So box A is good. Let's work on a box 2. Box 2, we have a negative sign in the front, and we have a B, which is our negative IH bar, partial x. And this is our P x, which is over here. And now we have x follows, this is guys x follows, and then we have f over here, like that. So this is our box number 2. Are we good so far? Now the box number 2 is our key things involved. Negative become positive, partial x. Now watch carefully. This is going to apply on two terms. One is x, one is f. That's why if your f is a constant, it doesn't make it needed. So this will end up with it like this. But when you have this term, you will end up with the two terms comes out. One is partial derivative with respect to x. So I only have f left over. The other one, I have x in the front and a partial x and f like this. So that is what we have over here. Did you see this term is exactly equal to this term, except we have an extra term comes out. So that is when we have it. Are we good so far? Are we good so far? Been able to follow? Okay. Any questions so far? Now we do a cancellation. Did you see we have a negative IH bar, x in the front, and a partial f over partial x? And this term cancels with this term here. These two terms cancels out. These two terms cancels out. In other words, this and that term cancels out completely. So then when I add these when box 1 and box 2 up, box 1 plus box 2, I only have IH bar like this. Okay. I have only an IH bar box like this. So now you compare with this term and with that term. Did you see both sides has f? So this box here, this box here is going to equal IH bar. So then, if we revert back to what we had before, so therefore, what we have x hat, p hat equals IH bar. So that's how we found a commutator. In other words, you see, this function is not used anymore. So essentially, we just compare these two terms. And we did not divide by f, by the way, because this f, it could be any function. So these two arbitrary, because this guy is arbitrary, so therefore the coefficient has to equal to each other. So therefore, this commutator is going to equal IH bar. So that's what we're getting. You know, doesn't matter how complicated a function you have. You always do like this. Assume a function in the back and just do the calculation. And that's how do we finish the calculation. You can cancel them out, so you have extra term. This extra term here is what is missed over there, like this. So this is exactly what missed. So in this case. So are we good so far? And in your homework and exercise, you're going to have a similar calculation like this. And this is my item number 2. Just show you how we do the calculation. And I just want to give you guys an in-class practice now. I think this probably is quite important. I want to give you guys a practice. This is an in-class practice. Okay, so I just want in-class practice. So it's kind of real. Yes, go ahead.
How do the IH bar partial, how do the two terms cancel? I'll put it that way.
Okay, let me write these terms out.
And, yeah, okay.
These two are the same. Makes sense? So that's why these two terms cancel out. They're exactly the same thing. Okay, good. And we're going to do in-class practice, so enter each one of you very, very good. Let's get started. I have one practice in the brackets is look like this. This time I have a function g like this. I have a function like this. Okay. So the g itself is a function of x. Had this been constant, sorry, you just get a 0, but this is the function of x. Folks, I give you 5 minutes to calculate how large this one is. You're going to follow exactly what I just showed you. You write on this particular format, A and B. This time A is px, B is a g. Okay? And then you do the B and BA, you do the exact same. You need to assume a function of course, this time also is f. And again, let me give you 5 minutes to do the calculation. Starts now. If you still have questions, please let me know. I will come over and talk to you guys.